Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like vector processors design principle, max performance estimates, programming for vector architecture. Let's get started. Slide 1. Introduction to vector processors. Let's begin by understanding what a vector processor is. Unlike traditional processors that execute instructions one at a time on a single data element, a vector processor applies one instruction to multiple data points simultaneously. This technique is called single instruction, multiple data, SIMD. Vector processors are highly efficient in handling large datasets and are used extensively in fields like scientific computing, graphics processing, AI, and simulations. How vector processors work. 1. Single instruction, multiple data, SIMD. The same instruction runs on multiple data elements at once, making computation much faster. 2. Efficient for repetitive computations, ideal for operations like matrix multiplication, where the same calculation is repeated across multiple data points. 3. Parallel data execution. Unlike scalar processors, which process data one step at a time, vector processors execute large sets of operations simultaneously. 4. Optimized memory access. Vector processors fetch and store data in bulk, reducing delays caused by frequent memory access. 5. Pipeline-based execution. Similar to instruction pipelining in CPUs, vector processors overlap computations, reducing idle time. Example: consider NVIDIA Tensor Cores in modern AI accelerators. They leverage vector processing to speed up deep learning and machine learning tasks, enabling real-time AI inference. Significance. Why do we need vector processors? Because they significantly boost computation speed in fields like cryptography, physics simulations, 3D rendering, and AI training. Their ability to process large data sets efficiently makes them essential in modern high-performance computing (HPC). Slide 2. Design principles of vector processors. The architecture of vector processors is specifically designed to maximize parallelism and optimize memory usage. Let's look at some of their key design considerations. Key design considerations. 1. Vector registers. Unlike general-purpose registers in CPUs that hold single values, vector registers store multiple data elements for simultaneous processing. 2. Vector instructions. A single vector instruction applies to an entire set of data, unlike scalar processors, which operate on one element at a time. 3. Memory access optimization uses stride-based memory fetching, which efficiently loads consecutive elements in memory. 4. Pipelined execution, similar to CPU instruction pipelining, but here, multiple vector operations run in parallel to boost throughput. 5. Chaining allows dependent vector instructions to overlap their execution, reducing delays and improving efficiency. 6. Conditional execution selectively applies vector operations to specific data points, improving flexibility. 7. High bandwidth requirements. Because they process large amounts of data in parallel, vector processors require high-speed memory access to avoid bottlenecks. Example: the Cray-1 supercomputer, one of the earliest vector processing machines, used vector registers and pipelined execution to achieve unprecedented computing speeds in scientific simulations. Significance. Understanding these design principles helps in building efficient parallel computing systems that can handle the massive processing needs of AI, simulations, and real-time data analysis. Slide 3. Maximum performance estimates of vector processors. The performance of a vector processor depends on multiple factors, including hardware efficiency, memory bandwidth, and instruction execution speed. Let's explore the metrics that determine the maximum potential of a vector processor. Performance metrics. 1. Vector length (VL). This refers to the number of data elements that a single vector instruction can process at once. A higher vector length means greater parallelism. 2. Vector Functional Units (VFU). These are specialized processing units within the processor that execute vector instructions simultaneously, improving computational efficiency. 3. Pipeline depth. The deeper the pipeline, the more instructions can be processed simultaneously, reducing idle cycles. 4. Memory bandwidth determines how quickly data can be fetched from memory to the vector processor. A bottleneck here can limit overall performance. 5. Peak flops, floating point operations per second, measures the maximum computational capability of the processor, often used in scientific computing. 6. Efficiency versus scalability. Efficiency depends on how well the processor utilizes its available resources, while scalability refers to how well it can handle increasing workloads. 7. Vectorization ratio. This metric tells us how much of a given workload is optimized for vector processing instead of scalar execution. Example: modern NVIDIA A100 GPUs achieve 19.5 teraflops, making them among the fastest vectorized AI accelerators. Significance: maximizing performance in vector processes requires well-optimized vectorization techniques, efficient memory handling, and effective instruction scheduling. This ensures they deliver peak performance in high-performance computing, HPC, AI training, and large-scale simulations. Slide 4. Vector processors versus scalar processors. Explanation. 1. Execution type. A vector processor processes multiple data points in a single instruction, making it efficient for parallel operations. A scalar processor, on the other hand, executes one instruction per cycle, making it suitable for sequential tasks where operations need to be processed one at a time. 2. Performance. Vector processors excel in parallel workloads like AI, simulations, and scientific computing because they handle multiple computations at once. Scalar processors, being optimized for single instruction execution, perform better in general-purpose computing tasks that don't require massive data parallelism. 3. Memory access. Vector processors are designed for high-speed bulk data processing, fetching multiple data points simultaneously, which reduces memory bottlenecks. Scalar processors rely on cache-based memory access, meaning data is fetched and processed in smaller chunks, which may introduce delays when handling large datasets. 4. Use case. Vector processors are widely used in graphics processing, AI computations, cryptography, and scientific simulations, where the same operation needs to be performed across large data sets. Scalar processors are designed for everyday computing, such as running an operating system, executing software applications, and handling regular computations. 5. Power efficiency. Vector processors are more power efficient for workloads that benefit from parallelism because they process multiple data points in one go, reducing redundant computation cycles. Scalar processors are optimized for single-threaded tasks, where power efficiency is achieved by executing one operation at a time with minimal resource overhead. Example to illustrate the difference. Vector processor example. NVIDIA's tensor cores in GPUs use vector processing to accelerate deep learning computations. Scalar processor example. A traditional Intel Core i5 CPU executing single-threaded software like basic word processing or system utilities. Key takeaway: if an application involves massive parallel computations, like weather simulations, AI model training, or 3D rendering, a vector processor is the better choice. For general-purpose computing, where instructions are executed one after another, a scalar processor is more efficient. Slide 5. Programming for vector architecture. Explanation. Vector processors are powerful, but to fully utilize their capabilities, programmers must apply specialized vectorization techniques. These techniques help convert traditional scalar computations into parallel vector operations, significantly boosting performance. Key vectorization techniques explained. 1. Loop unrolling. Instead of executing a loop one iteration at a time, loop unrolling processes multiple elements in a single iteration. This reduces loop overhead and improves efficiency. Example: instead of iterating through an array one by one, processing multiple elements per cycle speeds up computation. 2. SIMD extensions. SIMD, single instruction, multiple data, instructions allow the same operation to be applied to multiple data points simultaneously. Modern processors support SIMD via instruction sets like SSE, streaming SIMD extensions, AVX, advanced vector extensions, and Neon ARM SIMD instructions. Example: AVX 512 instructions in Intel processors accelerate AI and deep learning workloads. 3. Memory alignment ensures that vectorized data is stored in memory locations aligned to processor expectations, leading to faster retrieval. Misaligned memory leads to extra processing cycles, reducing performance. 4. Minimizing branching. Branching, if-else conditions, disrupts pipeline execution, slowing down vectorized programs. Optimizing branch-heavy code helps maintain seamless execution flow. Example: using branchless programming techniques improves vector efficiency. 5. Parallel reduction, used for aggregating large datasets efficiently. Example: in AI training, vectorized operations accelerate summation of large neural network weight matrices. 6. Auto-vectorization, modern compilers, such as GCC, Clang, and Intel ICC, automatically convert scalar code into vectorized code, reducing manual optimization effort. Example: a simple for loop can be auto-vectorized by the compiler if it follows vector-friendly patterns. 7. Threading in vectorization. Combining multi-threading with vectorized operations further improves parallel processing efficiency. Example: AI frameworks like TensorFlow and PyTorch use multi-threaded vector processing for training deep learning models. Example use case: Intel AVX 512 instructions are used in AI deep learning computations to speed up matrix multiplications. Significance: efficient vector programming maximizes hardware utilization, leading to significant improvements in AI processing, gaming, cryptography, and real-time analytics. Slide 6. Applications and future trends of vector processing explanation. Vector processors play a crucial role in high-performance computing, HPC, AI, and real-time analytics. Their ability to process large datasets in parallel makes them ideal for scientific, financial, and real-time applications. Key applications of vector processors. 1. AI and deep learning. Accelerates neural network training and inference, making AI models process data faster. Example: NVIDIA's tensor cores in GPUs optimize deep learning computations. 2. High-performance graphics. Real-time rendering in gaming and 3D applications relies on vector processing. Example: ray tracing in GPUs uses SIMD-based vector operations. 3. Medical imaging. Processes MRI and CT scans faster, improving diagnosis and treatment planning. Example: AI-assisted medical imaging relies on vectorized computations for high-speed analysis. 4. Cryptography. Speeds up encryption and decryption algorithms using vectorized operations. Example: ACE encryption benefits from SIMD-based acceleration. 5. Financial analytics. Handles high-frequency stock trading by running large-scale simulations. Example: hedge funds use vectorized Monte Carlo simulations for risk modeling. 6. Weather prediction and climate modeling. Processes complex climate models efficiently. Example: supercomputers running global climate simulations use vector processors for rapid calculations. 7. Autonomous vehicles. Processes real-time sensor data from LiDAR, cameras, and radar. Example: self-driving cars use vectorized AI models for object detection. Future trends in vector processing. 1. AI-optimized vector processors. Dedicated vector chips are being designed specifically for AI model training. Example: Google's TPUs, tensor processing units, are optimized for vectorized AI workloads. 2. Quantum-assisted vector processing. Merging quantum computing with vector processors for next-general AI acceleration. 3. 3D stacked vector cores. Multi-layer chip designs enhance bandwidth and power efficiency in HPC. Example use case: NVIDIA's Ampere architecture leverages vector processing to accelerate deep learning for real-time AI-powered applications. Significance: vector processors continue to evolve, shaping the future of AI, high-speed simulations, and real-time data processing across industries.